Girls, good morning. எல்லாரும் நல்லா இருக்கீங்களா? படிக்கிறீங்களா? I hope you remember some of our lessons that we heard before your closing. Especially you remember the Schrodinger equation, I believe. So we will now see the application of the Schrodinger equation. We know the Schrodinger equation is the basic equation and important equation in quantum mechanics, using which many of the problems can be solved. Today we are going to see the problem of a particle that is existing within a box and how the particle's energy can be quantized. Similarly, their wave function. This particle in a box problem is the simplest but important application of the Schrodinger equation, which illustrate many of the fundamental concepts of quantum mechanics. I hope you remember the famous Schrodinger equation in one dimension, which can be written as minus h cross squared by 2m dou squared psi by dou x squared, which I have written as psi double prime x plus v psi equal to E psi. This is the Schrodinger equation in one dimension. You remember? So, now we are coming to the problem of a particle that is existing within a box. This box is having two boundaries at x equal to 0 and x equal to L. So, the particle can move along the x-axis and it can have only the limited energy. So, the potential energy of the particle is 0 within the box. The potential energy outside the box and at the boundaries, it is infinity. Do you see that? So, you see that we have written V of x, that is the potential energy, is 0 within the boundaries. That means at x, starting from x equal to 0 and x equal to L, the potential energy is 0 and it is infinitive at x less than 0, that is here, and x greater than L, that means in this area. So if the particle has to come out of this box, then this particle should possess infinite amount of potential energy. Then only this particle will be able to come out of the boundaries and be found anywhere outside the box. Until and unless the particle is having the infinite energy, it cannot penetrate to the area outside the boundary and it can exist only within the boundaries. So, this boundary makes the potential well for the particle and the particle cannot penetrate through this potential well. Psi of x equal to 0 at x less than or equal to 0 and x greater than or equal to L. That means since the potential energy is 0 within the box and outside it is infinity, the wave function will be equal to 0 outside and at the boundaries. Similarly, in this area outside and at the boundaries. So, psi of x will be equal to 0 at boundaries outside. Now we will see, now our work is to find what is psi within the box. That means within this potential well. So we are going to find what is psi within the box, namely within x equal to 0, within this area, that is between the boundaries x equal to 0 and x equal to L. Now we see that this is the famous Schrodinger equation, h cross squared minus h cross squared by 2m dou squared psi by dou x squared plus v psi is equal to e psi. We are now finding what is the wave function that the particle can have within the box. Therefore, we know that within the box, the particle is having zero potential energy. So when we substitute zero potential energy in this term becomes zero. Therefore, the Schrodinger equation reduces to minus h cross squared by 2m dou squared psi by dou x squared equal to e psi. And just rearranging the equation, we will end up in this equation 5. What we have done? We have kept only dou squared psi by dou x squared this side, taken 2m this side. So denominator will go as multiplier this side. So it will become this side. We will have only psi star, dou dou squared psi by dou x squared, which is equal to minus 2m by h cross squared by into e psi. So this is minus 2m by h cross squared into e psi. So bring this side and make it psi squared x dou psi squared by dou x squared plus k squared psi x equal to 0. This equation, just taking this term, multiplying, and this comes as denominator with a minus sign taken to this side, and k, what is k squared? The term minus 2m by h cross squared into e is k squared. So in the place of 2m e by h cross squared, we have just replaced a k squared. So the general equation for this kind of equation, a double differential equation, can be written as psi of x equal to a sin kx plus b cos kx. So where this a and b are constant to be determined by the boundary condition. Now we will take the first boundary condition where psi will be equal to 0 at x equal to 0. This is the first boundary. So there are two boundaries, x equal to 0 and x equal to L. We will first apply the first boundary condition, x equal to 0, and find what is the wave function. So the previous equation, in the place of x, we just substitute the value x equal to 0. So psi of 0 will be equal to a sin k0 plus b cos k0. So sin 0 will be equal to 0. So this term will become 0. But cos 0 is not equal to 0. It is equal to 1. So it will be equal to b. So psi of 0 will be equal to b. But according to our condition, the psi should be equal to 0. In order to make psi equal to 0, we need to assume that b is equal to 0. So in that case, the psi will be equal to 0. Now we will apply the second boundary condition, x equal to L. So in the place of x, we will apply L. So psi, here actually it is L, is equal to a sin k L. and there should be b cos kl, and because we have assumed b equal to 0, this term will become 0. Therefore, only this term will exist. Therefore, psi of L is equal to A sin KL. But according to our condition, psi should be equal to 0 when we apply this boundary condition also. Because we have not assumed A to be 0, this term will not be equal to 0. Otherwise, when will it become 0? Only KL assumes the values of pi. It can be pi or 2 pi or 3 pi, then it will lead to 0. In that case, psi will be equal to 0. So, the condition psi to be 0, this term should be equal to n pi, where n can assume the values 1, 2, 3, etc. So, KL is equal to n pi. We know k squared is equal to 2me by h cross squared, and k is equal to root of 2me by h cross squared. If we are to find what is e from this equation, then we need to place where k is with n pi. So in the place of k squared, we'll just put n squared, pi squared, and here is L. So it will come to denominator as L squared. So rearranging this from this equation, we will get E is equal to h cross squared pi squared by 2m L squared into n squared. Just work it in a paper, you will get this expression. And if you substitute in the place of h cross h by 2 pi, then you will be ending in this expression h squared by 8m L squared n squared. So this is the energy value of the particle that is existing within the box. Depending on which state the particle is existing, we can find their energies distinctively. For example, suppose the particle is existing within the boundaries between 0 to L at the ground state, then n will be equal to 1. So, in the place of E is equal to h cross squared pi squared 8 2m L squared. In the place of n squared, just substitute the ground state value, that is n is equal to 1. So you are getting pi squared h cross squared 2m L squared. Suppose the particle is existing in the first excited state, then n will be equal to 2. So in that case, energy will be E2, which is equal to n squared, which is 4 pi squared h cross squared 2m L squared. Suppose if it is were to be existing in the second excited state, then the energy equation will be equal to 9 pi squared h cross squared 2m L squared. So thank you girls. The time is getting over. Till now only I can record. I will see you in the next video. Thank you for listening. I hope you understand. If any case, please feel free to interact with me.